All right. Hope you guys had a good spring break. Enjoyed the wonderful weather. We had good weather here the week before, right? Not so much during spring break. And now you're ready for that long grind because we're done with all those pesky vacation days for the year.
Oh, yeah, those make me so sad.
Yeah, I know. So we are studying chemistry, and today we're doing chapter 18, which is where we're going to learn about redox reactions and acids and bases. So acids and bases, some examples of acids and bases. The top things are acids. We have pickles. What do you pickle stuff in? Vinegar. And vinegar is acetic acid. Excellent. Let's change to something I can write with. So that's acetic. Uh-oh. I don't know how to spell acetic. You can tell I'm not a chemist by profession if I don't know how to spell acetic. And then we have a toilet cleaner, and we have Coca-Cola. How many people knew Coca-Cola was an acid? Yeah. It's poison? Right. You've probably seen the old internet meme about how bad Coke is for you. You can use it to clean your toilet bowl. You seen that?
Isn't it just because it's an acid?
It's because it's an acid. That's right.
I don't know, so most carbonation what makes it an acid?
It's carbonic acid, I think. Or is it carbonic or phosphoric? Don't remember. It's one of those two. They used to call them phosphorus. That's why. But we say carbonated soda. So that's why you can clean your toilet with Coca-Cola, because it's acidic. What else is acidic? All of these citrus fruits. And when they send you that thing, you should never drink Coke because you can clean your toilet bowl with it. It's so harsh. They don't mention, and you could clean your toilet bowl even better with lemon juice. Right? Because they don't want to, scare you away from lemon juice. That's good for you. Now, the funniest thing, I saw a website about trying to get your body chemistry more basic. Basic is the opposite of acidic. And it had a list of things that you could eat that were basic. And it said citrus fruits. And, I'm sitting here scratching my head, and the person said, it seems like it's acidic, but it's really basic. And I'm like, you are basic. Because it's definitely acidic. Okay. Yeah, I know. People who make those memes are generally not the sharpest tools in your sharp. Okay. People who mess up their idioms are generally not. I'm intentionally doing this, not running with a brick to the top level. Anyway, so things that are basic. Baking soda. We used baking soda in our last lab, right? Mm-hmm. That was a basic thing. Yeah, we did. Yeah. Oh, no. Was that? Oh, no, that was the one that was missing. You're right. It was supposed to be there. Hello, Brittany.
I'm not stupid.
Okay, soaps. Last lecture, we had the soaps. Remember, soaps had one end that was polar and one end that was non-polar. And the polar end attaches to water. The non-polar end has induced dipole attraction, very weak, to grime, and that's how it cleans stuff. Well, soaps are basic. And Drano. What does Drano ideally do? By dissolving your hair. Yeah. So don't use it as, since it's a base, just like soap, don't replace them. Because it's a lot harsher. So we have acids and bases. And if you go somewhere like, Mono Lake, it's very basic, which means that it's very slippery feeling.
So Drano was a base, right?
Yes. So what's the difference in an acid and a base, right? Just showing you these are acids, these are bases really doesn't help you any, right? You can't use that in any way, just knowing, oh, this is an acid, this is a base. So we start with a definition. Now, there are a couple different definitions for acids and bases, and the one our textbook is using is the one on hydrogen donor or acceptor. And so an acid is something that will give up a hydrogen atom. A base is something that will accept a hydrogen atom. So we're talking about chemical changes if we're giving up a hydrogen atom or accepting one. Now, I said atom. That wasn't really precise. What's the word up there instead of atom? Ion. So what's the difference in an atom and an ion? The charge, yeah. It's the number of electrons they have. So the hydrogen atom is nice and in focus. The hydrogen atom has a proton in the nucleus. Now, this is one isotope. This is your standard hydrogen 1 isotope. And it has one electron. Now, this is not trying to show what they're doing. After all, what is the electron doing in the hydrogen atom? Yeah, don't really know, right? We know it's doing some kind of orbit. We don't know what its path is. We don't know how it's moving. We can calculate where it's likely to be found. That's it. So that's a hydrogen atom. If you're going to make it a hydrogen ion, what are you going to do? Do what? Yes, take away the electron. So you just take away the electron. Anybody know that sign? Jocelyn does. Oh, actually, in chemistry, you're right, it is, but in math.
I've never seen it.
It means it's defined as.
Why don't you just put equal?
Hmm?
Why don't you just put equal?
Because the definition is stronger, shall we say, than is equal. You know, I'm not going to go into nomenclature things. So the hydrogen ion is just a proton. So when we said here a hydrogen donor or a hydrogen acceptor, we could have said a proton donor or a proton acceptor. It would have been exactly the same meaning. Except for when you say proton, then you tend to think maybe you took like a carbon atom, you took a proton away and said, here, you can have this. That's not what we're talking about. So let's see some, well, this is something you should probably memorize. Just so if you ever have a question, like coming up in a clicker question, you can use it. So, bad. Base accepts, acid donates. So what is the base accepting? Yeah, proton or H plus, and the acid is donating an H plus. So let's see this in action. Here's an interaction between HCl, that's a hydrogen bonded to a chlorine, and H2O, what we normally call water. So in that action, the green is the chlorine atom, and the blues are hydrogens, and the red is oxygen. So just describe for me in words. I know we can all listen to me, but I want to listen to you. What's happening? What is going on in this picture?
It's like HCl is giving away.
Hydrogen.
Okay, between the two people in the front row, HCl is giving away a hydrogen. Now, based on what we just learned, that BAAD, which one is a base and which one is an acid?
First one's an acid. Or HCl.
The first one is the donator.
Okay, the first one is the donator. And so which one goes with D? Acid. So that means the HCl is the acid, and the water, H2O, is accepting, and so accepting is the base. So in that case, we had HCl, which we call hydrochloric acid, because it's an acid. It's a pretty strong acid. What that means is it really doesn't care to have the hydrogen nucleus. The chlorine is very high on our electronegativity. Remember we saw, you can look at the picture back there, the bottom left corner was low electronegativities, the top right corner of the periodic table was high electronegativities, and chlorine is up there in the top right corner. So it really, really wants an additional electron. But it didn't care so much to have the proton that came with it. And so it's easy for the chlorine to give up the proton as long as it keeps the electron. And so that's what happened here. The chlorine kept the electron, so now it's a Cl minus. And then the proton came over and we had hydronium, H3O plus. It's a plus because it didn't get the electron that came with the hydrogen, it just got the hydrogen. Why would hydrogen bond to water? Because what? Here's the important thing. Water is a polar molecule. Has a positive side and a negative side. And so the hydrogen comes around, it's positive. We have a negative side for the water molecule. The hydrogen and the negative side of the water molecule will be attracted in a dipole, that's the water, ion attraction. And so that's how you can make this non-neutral hydronium molecule because it's a dipole. Here's another one. What's going on in the picture, again, on the left side? What's going on in this picture here? Okay, the water is giving away a proton. So if the water is giving away a proton, donating, it's an acid. And the NH3, the ammonia, is the base. Now, the thing I want you to note here was, what was water on the previous slide? It was a base. Here it's an acid. So water can be both an acid or a base. As you might guess, if it can be both an acid or a base, it's a weak acid or a weak base. It's not a strong acid like hydrochloric acid. So what did this form? Hydroxide, that's the name of this thing. And, okay, I don't remember the difference in ammonia and ammonium. One of these is ammonia, one of them is ammonium. I should know better. So this here, I didn't write the name, but okay, going with that hydronium, I'm going to go with this as ammonium. And this is ammonia. And if my spellings are off, I'm sorry. Just because you have the ium for adding the extra hydrogen. Now, for the real trick, and you might have seen these. These pictures are all in your book. That reaction can go the other direction. We can have the ammonium give up a hydrogen to the hydroxide and form the starting things. So the reaction can go both directions. In this case, looking on the right-hand side now, which one's giving up, donating a proton? The blue, well, yes. The ammonium. So since it's donating, what does that make it, acid or base? Acid. So this is an acid. And what is the one that's receiving? Base. So we had the hydroxide as a base, the ammonium as an acid. Put those two together because when you actually mix these things, the reaction will go both directions. It will reach a balance between that, so that the amount going this direction is the same as the amount going that direction. And so now we can see that the water was an acid and the ammonia was a base, but the hydroxide is a base and the ammonium is an acid in the reaction. So what's going on with these acid-base reactions? Hydrogen atoms are moving across. Now, if you were taking a higher level chemistry class, we learned that it doesn't have to be just a hydrogen. It's a positive ion donation is what really would be the acid. But for our level, it works fine. Just talk about these. So our first clicker question. When water behaves as an acid, what does it lose?
That's so dumb.
I forgot what the thing used.
The channel?
I'm
We're channel 33 if that's what you mean.
Session ID.
The session ID is WebFizz. Haley, Carmen, Hannah, Brandon, Candace. Oh, Candace just answered. Haley, Hannah, Brandon. Brandon. It's all up to you.
It keeps logging in.
All
I forgot
up
my password.
to you. All up to you. So are you going to get in?
You can just go.
Okay. So we had 10 that said hydrogen ion, 0 that said hydrogen atom, 2 that said an electron, and 2 that said water can't behave as an acid. Candace, give us your reasoning here.
Well, I said C
Okay.
because we were talking about. I thought we were talking about electrons that were being donated.
Okay. It was hydrogen atoms moving across. So the correct answer was A, the hydrogen ion. Now I just said hydrogen atoms moving across, but when you have the choice of hydrogen atom and hydrogen ion, there's a difference between the two. The ion, the electron's not moving with it. And that's the important distinction. So when I say hydrogen atom, yeah, it is a hydrogen nucleus, which we generally say is a hydrogen atom. Like we say in the sun, we're fusing hydrogen into helium. Well, we have protons colliding and forming alpha particles is what's really happening. But we use those terms. But when you have the option, go with the, and everyone did, go with the technically correct there of the hydrogen ion. Okay, so a salt. Everybody's familiar with table salt, so we got a picture here of table salt. But salts are much more than just table salt. Salts are the precipitate you get when you, well, I say the precipitate, here it says the ionic compound, formed when you have a reaction between an acid and a base. So for instance, if I were to take from our first slide an acid like a Coca-Cola, and I was to take a base like, well, were any of our options of a base liquid form? I don't think any of them were liquid form.
Liquid soap.
Liquid soap, okay.
Body wash.
Let me go with sodium hydroxide, which we used in lab last week or week and a half ago, whatever. If we mix those two together, then when we put them in water, because water can be either a weak base or a weak acid, we put a strong acid in the water, we're going to have the hydrogen removed from whatever the other piece is. If we put a strong base, we're going to have the a hydrogen accepted. And what's going to happen is we're going to have the other pieces floating around. So if we take something like cyanide, okay, we probably shouldn't, but hydrogen cyanide and sodium hydroxide, and we mix them together, we're going to have the HCN becomes H plus CN minus when I put it in water. And the NaOH becomes that when I put it in the water. And then what happens is we have a strong attraction between these things. And so this, if we put those together, we're going to get NaCN plus, what do you get when you put an H and an OH together? You get water. And so that's the reaction that's shown in the first line. You have this salt that's formed that is this part, and then you have the water. So nobody wants to eat sodium cyanide, right? That's not what we use for table salt, but it's a salt. Sodium nitrate's a salt. Sodium nitrite is too. Potassium nitrate, calcium chloride, sodium fluoride. All of these are salts. What's the most common salt besides sodium chloride that you eat? They often put things in here. See, this says half the sodium of table salt. How do you have salt with half the sodium? You have to put something else in place of sodium. So instead of having sodium chloride, it's not shown here, but they took, you can see here, it tells you, it's iodized and has potassium chloride. So iodized salt means that you have, if you look up there, you see I is in the same column as Cl. It's in the halogens. And so you're replacing the chlorine with iodine if it's iodized salt. And so you have like sodium iodide. And so this half the normal amount would have some sodium iodide, and then it has potassium chloride. Potassium is in the same column as sodium, it's just one below it. And so it's replacing the sodium with potassium. Chemically, the bonds aren't quite the same strength, but they're still the same types of bonds. In the body, once again, they're going to interact a little bit differently. They're of the same type, but they may interact more or less strength. And so, having these different atoms is going to make the body behave a little different. So what is the reason people want to avoid sodium? Yeah, high blood pressure is the big reason. My brother's father-in-law actually is having his surgery to remove some tumors delayed. It was supposed to first been last week, and then it was supposed to be this week, and now it's the week after, because his blood pressure is too low. And so what are they doing? They're pumping him full of salt, because that salt is then going to, in theory, raise his blood pressure. What do you suppose is really happening to him? Well, you guys probably are just too young. It used to be like when football players were out there practicing and getting dehydrated, they would take salt pills, because the salt makes your body absorb water into the tissues. And so he's gaining a half pound a day in water weight because of all the sodium they're having him take. But not the purpose here, but these chemicals have reactions in the body and they make a difference. So here is a more interesting example of an acid-base reaction making a salt. So we have HCl, hydrochloric acid, and we have pseudoephedrine. What's pseudoephedrine? Okay, it's I believe it's antihistamine. It's also a precursor to methamphetamine, yeah. And so these days, it's harder to get a hold of this stuff because people like, I never watched Breaking Bad at all, but chemistry teacher, apparently, in that TV show, takes things like pseudoephedrine and makes methamphetamines and makes a lot more money than we can as teachers. But aren't you glad your dad didn't do that? We need to raise the salary. Okay, so So here we have a reaction between hydrochloric acid and the pseudoephedrine, and it makes a salt. You notice this here, that double dot. What does the double dot mean? Okay, they're valence electrons. They're electrons there that they're forming a pair, and that means you're going to have a generally negative charge there because you have the two electrons hanging out together. And then because the hydrogen chlorine separated, the positive hydrogen was attracted to that negative charge and formed a bond, but because the hydrogen didn't come with its electron, it came just as a hydrogen ion. Then we have a positive charge, and then the chlorine has an ionic attraction there. And so we have this pseudoephedrine hydrochloride. All right, second clicker question. Oh, sorry. It's asking me if I want to install software. Thank you. Not during class. So you can answer now. What salt forms from the reaction of hydrogen chloride, which is HCl, and potassium hydroxide, which is KOH? So without using your phone, you got yourself logged in.
Yeah,
Still not answered.
I'm thinking. Am I the only one?
No, there's others. Oh, you're still thinking about your answer.
Yeah.
Okay.
Which salt forms? Got it.
Maggie, Jocelyn, and Raquel. Okay, Jocelyn and Raquel. It did take your answer. There we go. All right, so we have here 5 for potassium chloride, 0 for H3OCO, 1 for potassium water, and 9 for potassium OH2Cl, and 0 for sodium chloride. It is good that nobody conjured a magical sodium that's not in our equation.
So who's really guessing?
Okay, Stacy.
I answered A because in balancing equations, the H2O takes care of the O and the two H's. Sodium's not in it, and then all the others have either O or H. All that you're left with is K's.
Very good reasoning and correct. Okay, so 9 people said KOHHCl. What did those 9 people do?
Yes.
Yeah, they just added them together.
Yep.
But note that I had shown you plus water. So you have to take the H2O out of that. So that means you take these two out, the H2O, and it's KCl. Or, and the way you're supposed to think about this is when you have your acid donates, and so it gives up an H. So one of those was giving up an H. And then we have the base accepts, one was accepting the H. And so we had to have, well, HCl you should recognize is a strong acid. What makes a strong acid? Well, you have something from the left column and something from the next to last in the right column, strong acid. And so the H came off, leaving the Cl to grab that K, and the H went over. All right, So good answer, good answer. Now this here is just 2 slides to say something simple. If you have a really strong acid or a really strong base, it will completely ionize in water. So in this picture, this young chemistry student is putting hydrogen chloride gas into his water. And so hydrogen chloride being a very strong acid, it's going to completely separate. So in the water, you have a bunch of Cl's that are all by themselves. Don't have the H with them. Where'd the H go? To what? To the waters. So we have these ones that show red, are showing red because they accepted hydrogens, and thus we have completely dissolved. Weak acids and weak bases don't completely dissolve. So here he's mixing acetic acid. Okay, there we can see how to spell acetic acid. I spelled it right. Yay. He's mixing his vinegar with water. Oh, she is. Got to make sure I'm correct on these things. And so here you can see some examples where we have very few of these CH3O2s. We have some that are neutral, C2H4O2. And we have a very small amount of the H3O that was hydronium. So here's what acetic acid is and the acetate ion. So the thing we started with is what I put in green. It's not completely dissolved, but we do have some of the acetate ion, what I put in the black. Did you have a question, Renee?
Yes. Okay, so I'm looking at the picture, and I know that there's all these, water molecules everywhere, but not a lot of the other ones. So if there are less acetic ions,
The acetic acid is not an ion, but the acetate ion is an ion. So I'm not sure what you're talking about. You could have meant either one.
so
There's not very much of this formed.
okay, so of that one, so do there have to be the same amount of ions being transferred or donated?
Okay,
Returned?
if I'm understanding your question correctly, and I may not be, what you're going to have is a balance based on how strong the acid or base is between how much was converted and how much was not. So if it's a really strong acid or base, you're going to have the whole thing was separated to produce this side of the equation. That's what would happen if it was a strong acid or base. But since this is a weak acid or base, only a small amount had the product formed. So it depends on the strength of the acid or base, how much product is formed. Now, with the forming of the product, since this is a 1 and a 1 here, we don't write the ones in our balanced equations, then we're going to have exactly the same number of hydronium ions as we have the acetate ion. But that wouldn't be the same as the number of acetic acid atoms. Is that what you were asking?
I'm not sure.
Okay, then that's what I'm answering. We may or may not do the lab with the making a battery for lab this week. But batteries, back in the day, we had to put acid in our car batteries. Why do you put acid in the battery? Because you have a reaction occurring at those two pieces of metal. And it's because of the acid, the effects of the acid, that those reactions occur. And so if you have a weak acid, you don't have much reaction. A strong acid, you'll have a strong reaction. So how bright the light bulb is indicating how quickly the reaction is occurring. and thus the strength of the acid. So in these pictures A, B, C, which one is the strongest acid? B, because it's burning the brightest. It didn't tell us what the acids were in each case. And you see they were just clear liquids as far as we can tell in all cases. But they're different acids, and the stronger acid is going to have a faster reaction, producing more current. Now, we've seen that water can be both a base or an acid. And when you have just pure water, when you put water in water is what I was going to say, but that sounds silly. When you have pure water, you will have a certain amount of water molecules that split up into an OH and an H3O. And so in this case, you had water. We could say one of these molecules was an acid and one was a base. Which one was the acid?
Water.
Which one? The first one or the second one? You are correct, of course, Brittany. But which one of these two, let's call them A and B, which one's the acid?
The B. No, the A.
Acids donate. And so, as luck would have it, A was for acid and B was for base. Yes. I put them up there randomly, but I'm glad that they turned out that way instead of, so A stands for base and B stands for, yeah. Yeah, so that wouldn't have worked out so well. So when you have just pure water, there's a certain amount of OH and there's a certain amount of hydronium. And so we measure the concentrations, and of course this goes to my answer to Brittany. The concentration of the two products, because it had a 1 in front on both sides, should be the same. And it turns out that concentration is 6 zeros, 0.6 zeros, and a 1. Or as we write it in scientific notation, 10 to the minus 7th molar. So the molar was moles per liter. So we have 10 to the minus 7th moles of OH per liter of water. And 10 to the minus 7 moles of hydronium per liter of water. So it has both acidic and basic behaviors, and it's this here, the concentration of OH, we have a special name for that. Anyone want to take a shot, just a flyer, shot in the dark? No, the special name for the concentration of hydronium.
No.
The pH.
Okay.
The pH is a measurement telling us about the concentration of hydronium. And if you have something that's balanced, like water, then it should have the same concentration as water. So this scale here is showing us it's balanced. We have the same concentration of OH minus as we have of H3O plus. And we call that neutral. And notice the concentration is 10 to the minus 7. So how do we get the pH from that? The pH is defined with this equation. I don't remember what the P stands for. My teachers never actually said pH stands for this. The H stands for hydrogen. I don't remember what the P stands for. And so the pH is minus, notice that minus sign, log base 10 of the concentration. So we have that question in the red box, what is a log? And of course, we're not looking for funny answers. Well, you cut down a tree. Who's comfortable with this mathematical function log? A few. Okay, so since you're comfortable with it, are you comfortable explaining to everyone, Valerie? Okay, that's fair enough. So what the log means is what power would I have to raise 10 to get this value? So if we look at pH equals minus log of 10 to the minus 7, the answer for log of 10 to the minus 7 is what power would I have to raise 10 to get 10 to the minus 7? Minus 7, but yeah. Right, it was a pretty simple answer there. 10 to the minus 7 is 10 raised to the minus 7. And so that means the log of 10 to the minus 7 is just minus 7. Then that minus sign that was in front of the equation converted it to plus 7. So if I have a pH of 7, that means that the concentration is equal to 10 to the minus 7. So what if I have more H3O? If I have a higher concentration, what's going to happen to the number?
It'll go up.
It'll go up. So what does that do to the exponent?
Makes it go down.
It makes it go, now up and down starts to get confusing in this case. You may have been correct or incorrect with the same words. So it makes it go to a bigger number, which means for a negative value, a bigger number is a smaller negative.
Yeah.
And so, yeah, good. So you might, if you have a higher concentration, it might be, say, 10 to the minus 3. What would the pH be if it was 10 to the minus 3 for that concentration? It'd be 3. Right, not very hard to see how these work. So a pH that is closer to 1 has a higher concentration of the hydronium. A pH that is closer to 14 has a smaller concentration of hydronium.
Why does the scale end at 14?
I believe in theory you could go further.
So I just need to find some elements.
Yeah, we have a table here or a graph that shows some pHs, and you can make things with obscene values. So something that has a higher concentration of hydronium is acidic. So that means if pH is less than 7, remember 7 was neutral. If pH is less than 7, then it's acidic. And if it is more OH, then you have a pH that's going to be greater than 7 because you have a lower amount of hydronium. And that's basic. So you can determine if something's basic or acidic by looking at its pH. And that's the lab we're more likely to do this week, is the one where we're going to make some cabbage stew and use that to determine the pH of different materials. Don't worry, we don't have to drink it. So this here is showing how we can, once again, look at the balanced. If we have the same amount of hydronium and hydroxide, then it's balanced and it has a pH of 7. If we have more hydronium, then it is more acidic. It has a lower pH. If it has less hydronium and more hydroxide, don't you like hydronium and hydroxide? Is it clear to you which one's which? No?
Hydroxide's the one with.
The first one. The H3.
Nope.
Is this the second one? The OH? Hydroxide?
One's a 50.
It's got, yeah. Oh,
So that's hydronium versus hydroxide.
I got it.
Okay, she's got it. So if you have more hydronium, less hydroxide, more hydronium, less hydroxide, more hydronium, then it's this one. This one has more hydronium because it sank down and it's an acid. Good. If you have more hydroxide, then it goes the other way and it's a base. Okay, so probably our last clicker question. As sodium hydroxide, NaOH, is added to water, the hydroxide ion OH minus concentration does what? There we go. Okay. We had pretty even split. Turn to your neighbor and discuss what should be going on here. What happens with the NaOH when you put it in water? Notice I have plus H2 on both sides. Usually we just put parentheses AQ to say it's in water, but I want to be explicit.
Well, but
I put A because I figured.
But I said, and I didn't know. Oh, okay.
My life would have ended on answering this question correctly. That'd be really important.
I would probably die. The entire front row was just sitting here like. He's
Wow.
like, stop.
It says Valerie's name on this card.
Oh no, Valerie. Oh, Valerie. And I don't know how to love you. Dear.
I just need to. All right, so I think this is positive.
Okay, let's answer this a second time and let Valerie explain it to everyone. Wait a minute. There, now you can answer. Skylar got the first two answers in. Go, Casey. You're the only one who hasn't answered.
Oh.
Seriously. Yeah. Well, it didn't show me.
It was something like 6, 7.
Well, that was the first time. I got that written down. But it didn't show me the second time. It just says 000, but it says 15 people responded.
Be higher.
7
We
was
thought
for
for a
B.
second.
yeah, it's like 6,
8 was
7.
6, and then whatever else was remaining was C.
Okay.
So 6, 7, 2.
So you're saying 6 like that? Okay.
The only one who.
Valerie, explain your reasoning.
I really had no clue. I just assumed that because it has so many ions on one side, it has to have some amount of ions on the other.
Well, what's going to happen to the NaOH when we put it in the water? It's a pretty strong base, so it's going to do something. What's it going to do?
Attract ions.
The first thing it does is actually break it apart. It breaks apart into Na plus OH minus. So what happens to the concentration of OH minus when we have this reaction? If you're going to produce OH minus, what is that doing to your concentration? It's increasing it. That's right.
No, I shouldn't have changed D.
Okay, so if the OH goes up, does it become, well, do we have a base or an acid if the OH goes up? It's going to be a base. Because remember, if the H goes up, it's an acid. If the H3O, if the OH goes up, it's a base. And so this here is a strong base because it caused the OH to go up. Okay, we are out of time. So go on and have yourself an awesome